And I'm going to start sharing my screen. And I'm going to go to, whoops, that says Jan 2 instead of January 25th. Let's make sure it's clear that this is January 25th. That introduction, if you did not yet submit it in Blackboard, please do. I just want to make sure that everybody can submit a picture of something handwritten in Blackboard before that first test or quiz. Homework 1 is due on Wednesday. Today we're going to look at cardinality, equal and equivalent sets. And we're going to start looking at a subset of a set. That first quiz is going to be on Wednesday, which is the 29th. It will be due on Sunday night. It will be a 15-minute quiz. It will have 10 questions from Chapter 2, Section 1. Before we get started with any of that, when I looked this morning, several of you were already in my labs, but not everybody. Please register in my labs. Even if you don't have the access code yet, or if you're not ready to pay for the access code yet, use that 14-day free trial so that you get some of that homework under your belt before that first quiz, and also so that your name is in the grade book, so that even if you're doing the pencil and paper homework, I have a place to store your homework grades. Before we get started, does anybody have questions on anything, either anything from in the homework, anything that we did in notes, or anything, not too much life in general? I'm not a counselor. Any questions? If not, quick recollection on my part. So far this semester, we've looked at what a set is, a well-defined collection of objects. We had some questions that asked us to decide if something was a set was well-defined or not. Then we looked at ways of writing sets. We said we could describe what's in them. We said we could use a roster, which is in braces with commas in between the elements, and we could use that set builder notation. In that set builder notation, we talked about the difference between the natural numbers and the whole numbers. We looked at the symbol for element of, and we looked at our symbols of inequality. We also defined the null or empty set. So being there are no questions, I'm going to go on the assumption that everybody's comfortable with that. And then the last thing that, therefore, that we're going to look at in this first section of Chapter 2 deals with the cardinality of a set. And when we talk about the cardinality of a set, it's the number of elements in the set. Before we go through and find some cardinalities, let's look at the notation. If S is my set, we're going to have a lowercase n with that set S in parentheses, and that's going to be the cardinality. The cardinality is a whole number. Realize that when we try to find the cardinality of the set, we're not going to get another set. We're going to get the number of elements. When I look at that idea of cardinality, that notation n, that n in my mind reminds me that that's a number that I'm looking for. So those are the quote unquote rules for cardinality. If everybody's got them all down, I'd like to look at a few examples. Can I scroll up?
Yeah.
Great.
Yeah.
And first example, if D is the set of days of the week, what's the cardinality of D?
7.
Beautiful, 7 days in the week. If A is the set of letters in the alphabet, what's the cardinality of A?
26.
Beautiful. If C is the set C, comma, A, comma, T, what's the cardinality of C?
3.
Beautiful. If D is the set D, O, G, no commas, what's the cardinality of D?
1.
One word. Beautiful. And if L is the set of letters in the word engineer, what's the cardinality of L? And here, be
8.
careful, because remember we had said when we're looking at a set, nothing counts twice.
5.
So we've got
Uh,
E-N-G-I-R, so it's 5. The letters that repeat only count once. Sometimes with these, I find it's easier to list it by roster before I count. And let's look at one more. Let's say T is the set of all T such that T is an element of N and 3 is less than or equal to T is less than 5. What's the cardinality of T? First of all, before you answer that question, let me make sure that everybody remembers how to read this. T is the set of all T, so we're using a variable to represent what's in my set. T is a natural number, that's what that first part says. And then we've got 3 is less than or equal to T is less than 5. Sometimes with ones like this with inequality, some people find it easier to list what's in the set first. The set does include 3, 4, but notice there's no equal sign here, so we're not including 5. And so when I go ahead and count how many things that are in there, I get 2. And then one more. What's the cardinality of the empty set?
One.
0.
Is it
0.
1? Oh,
Let's
never mind.
look at the empty set. Is that set with nothing in it? So the number of elements, the number of elements in it is 0. There's nothing in there. All right, for cardinality, we're just counting how many things are in that set. If so, I'm going to turn the page. The next place we're going to go are equal sets. And equal sets are kind of what they sound like. They have exactly the same elements. And so let's say D is the set three letters, D, O, G, the letters in the word dog. And let's say G is the set G, O, D, the letters in the word God. Is D equal to G? Do they?
Yes.
Yes, they have
Yes.
exactly the same elements. Again, order does not matter. They just need to have the same things in there. Another example, let's say C is the set C, A, T. And let's say K is the set C, A, T without commas. Is C equal to K? Do those two sets have the same elements?
No.
No. Beautiful. The first set contains three letters. The second set contains one word, so they're not equal. Where it gets a little bit different is if instead of talking about equal sets, we talk about equivalent sets. And I know in regular talking, a lot of people use the words equal and equivalent interchangeably. It is not the same with sets. Equivalent sets do not have to be equal. We're going to say definition that two sets are equivalent. And the initial definition is kind of wordy. We're going to say that two sets are equivalent if there exists a one-to-one correspondence between their elements. Two sets are equivalent if there exists a one-to-one correspondence between their elements. Two sets are equivalent if there exists a one-to-one correspondence between their elements. Sorry for the rustling. I need a cough drop. I'm not used to talking all day yet. So what does that mean? I'm going to look at the set D, which is D, O, G. And I'm going to look at the set C, which is C, A, T. And to say there's a one-to-one correspondence means I can match every element of the first set with an element of the second set. I can pair them up. So over here, if I look at it, I compare the D with the C. I compare the O with the A. I compare the G with the T. Everything in the first set has a partner in the second. Everything in the second set has a partner in the first. And so I can match them. Let's say I have the set P, which is the letters P, I, G, and I have the set H, which are the letters H, O, R, S, E. Sorry, I'm not real creative with filling in my sets. Here, can I pair every letter of the first with one and only one letter of the second, and everybody from each set has a partner?
No.
No.
Mm.
These two are equivalent. These two are not equivalent. And as I look at those two sets, depending on the set, if we have sets like this, which end, in order to decide if they're equivalent or not, can't I look at their cardinalities? The cardinality of D is 3. The cardinality of C is 3. They're the same, so I should be able to match them up. In the second set, the cardinality of P is 3. The cardinality of H is 5. And because they have different numbers of elements, they won't be equivalent. Those are examples of finite sets. And we're going to say that a set is finite if its cardinality is a natural number. You can count the elements and stop counting at some point in time. So you can count all the elements. And so if I look at all of those examples thus far, we could say that C, D, P, and H are all finite. You have to sort of be careful with finite sets because Mr. Blitzer uses a couple of examples that kind of blow your mind a little bit. Let's say, for example, that B is the set of all the grains on a beach. If we could stop time for an instant and not think about the continual change from things like erosion or stuff like that, B is finite. Its cardinality would be a very, very large number. I would not want to count all of the grains of sand on the beach. But in theory, it could be done. Another example, let's say A is the set of all x, such that x is less than or equal to 1,000,000, and x is a natural number. If I look at all of the numbers less than 1,000,000, I could count them. It would take a long time, but I could count them, so it's finite. Let's say I have B is the set of all x such that x is greater than 10 and x is a natural number. Could I count and stop counting all the numbers bigger than 10?
Yes.
Where would you stop? A million, a billion?
You don't know.
No, that's it. Just keep on going and going and going. So if a set is not finite, those are the sets that we call infinite. Those sets that never stop. And now that we've given a definition to this idea of infinite, I'd like to look at back step for a minute that idea of equivalent sets and show you why we can't just say that they have the same cardinality. Because sometimes we want to compare number sets. So let's say, for example, n is the set of natural numbers, and e is the set of even natural numbers. And so if I try to start listing what's in n, I'll have 1, 2, 3, 4, and I'm going to do the dot, dot, dot from there. If I start listing what's in E, the evens, it would be 2, 4, 6, 8, dot, dot, dot. And if I looked at it, and I know the first time I was asked this question, when I looked at it, I thought, wow, the natural numbers have twice as many numbers as the even numbers because it includes both the evens and the odds. However, because they're infinite sets, I'm not going to be able to really judge how many elements they have. I can't count them. I can't look at the cardinality. Can't I set up a one-to-one correspondence where I pair each natural number with its double? And if I go ahead and do that for any natural number, wouldn't there be a corresponding even number? And I'm going to go outside the braces, I'm sorry. For any even number, wouldn't there be a corresponding natural number? And I can set up that one-to-one correspondence. So even though they're infinite, there is a one-to-one correspondence. So we're going to be able to say that n is equivalent to E. But if anybody's interested, not all infinite sets are equivalent. Let's say, for example, I have the set n, and then I have the set of rational numbers. Which are usually abbreviated with Q. And they're usually written in set builder notation, set of all x, such that x can be expressed as a over b, where a and b are integers, but the denominator cannot equal 0. But I digress. If I look at the rational numbers, we use the set builder notation because if you think about it, I can't list them by roster. Because if I went 0, 1, well, in between them, I could put a half, but in between them, I could put a quarter. Between them, I could put an eighth, and I could keep putting more and more numbers in there. And so there's an infinite number of numbers in between any two of them. And so here there is no one-to-one correspondence. So that the natural numbers, well, they're equivalent to the even numbers, they're the same type of infinite. The natural numbers are not equivalent to the rational numbers because they're different types of infinite. So pretty interesting. When I look at the idea of an infinite set, is everybody familiar with the symbol for infinity?
Yeah.
And it's a symbol that represents a concept. It's not a number, it's not a value. You'll never equal infinity. You'll just talk about the idea of infinity, something that goes on forever. So that's the end of what's in that chapter 2, section 1. That's the end of what's covered in that first homework assignment. And those are the things that will be covered in that quiz that will be open on Friday. I'm going to, unless somebody has a question, I'm going to turn the page and start looking at what's in that next section of the textbook, chapter 2, section 2. Is everybody all right if I do that?
Yes.
I was
Yeah.
if you could go back up. Wait, you post these on Blackboard?
Yes, I do.
Oh, okay, never mind. Thank you.
I post them on Blackboard in 2 ways. As long as I remember to hit that record button, I post them as a YouTube and audio recording of the class, but I also upload a PDF document, which is just the printed words, the printed notes. Okay?
Okay, thank you.
So if you're worried about keeping up writing, if you feel like you can't write fast enough, just pay attention and you can get the written words later. Okay?
Thank you.
All right.
You mentioned a textbook. Were we supposed to purchase a textbook?
No, you have
Oh.
access to the virtual textbook in
Okay.
My Labs. Do you remember how to find the virtual textbook in My Labs?
Yeah, I purchased the 14-day free trial. Is that the one you're referring to?
Yes, and in
Okay.
there, if you look at multimedia on the left-hand toolbar, if you're in the home page, there's a place where there's a multimedia library, and in there you can get access to the digital copy of the textbook. You can also get access to like videos, just explaining things, stuff like that. If
Okay.
anybody wants a paper copy of the textbook, again, let me know. I have, don't buy it, just buy the access code. I have back issues of the paper textbook. I have so many back editions that if you want to borrow one from me, you can do that if you really want a paper book in your hands. Okay.
I'm looking at it right now. You said it's on the left-hand side when we log in.
Of the My Labs, yes. Let me show you real quick.
Thank you.
So I'm in Blackboard. In Blackboard, I'm going to go on the left-hand side to that My Labs. In My Labs, I'm going to go to My Lab Mastery and Course Home. And when I do this, I think in Student View, it shouldn't be that different. In this left-hand column, there's something that's called a multimedia library. Do you see where I am? And when I click on the multimedia library, we're going to be looking at chapter 2, section 2. Oops, not section 1, section 2. Gosh, my finger's too fat today. And I can open the multimedia textbook. I click that, it gives me a link down below. When I click on that link, it will take me to the page in the virtual textbook. And then you can hit an arrow to turn pages as you read through the section.
Okay. Thank you.
Let's see. Sometimes it doesn't pop up for me the first time and I just have to repeat those steps. I don't know why. Just sometimes, you know, in general, sometimes Pearson My Labs does it to me.
So we selected the set theory, right? And then we went on the section 2, basic sets of concept. Was that the one?
Yeah, the subsets is section 2. But if you go through, I'm going to exit out of my book here. And I'm going to go to the list of assignments. And when I look at the assignments, when you look at the homework name, that homework 1, homework 2, homework 3, homework 4, homework 5. Those just give you the order of the homework. But you see over here where it says 2.1? That means chapter 2, section 1.
Oh, okay.
It's chapter 2, section 2. And if you look from chapter 2, we're going to skip all the way to chapter 11. We're not covering the entire book. We're just covering four chapters in the book. And so in the homework name, it's the homework number, but then those 2 digits after, those 2 numbers after, well, that decimal after, what's in front of the point is the chapter, what's behind the point is the section. If you want to look things up in that virtual book, or if you want to borrow an actual paper book and look things up in a book. Again, if you want to borrow one, please let me know. Okay.
Okay.
So let's look at chapter 2, section 2, which deals with subsets. And what we're going to start doing is we're going to start comparing different sets. So let's first define what a subset is. We talk about the subset of a set. And in order to define what a subset of a set is, because we want to do this in words and not symbolically, we're going to say that we have 2 sets. So let's say if A and B are sets, and if every element of B is also an element of A, then B is a subset of A. So what does that mean? It means if I've got 2 different sets and all of the stuff in one set is also in the other set, we say that the one is a subset of the other. When I look at this, there's a symbol for subset. And it looks kind of like a funny looking C. And that it's a funny looking C tells me that it's contained in. And then it also has a little line underneath. And when I look at that line underneath, I don't know about you guys, but it sort of reminds me of like the little equal sign under less than or equal to, or greater than or equal to. So it's contained in or is equal to. So if I say that B is a subset of A, we're saying that everything in B, every element of B, is also an element of A. So I liken it to the idea that B is contained in A. Everything in set B is in set A. And so let's look at some concrete examples of sets so that we can put a little bit more meaning to this idea. Is everybody all right if I scroll up a little bit to show examples?
Yeah.
So, whoops, go up there. It doesn't want to move up all the way. First example, I'm going to give you a whole bunch of sets. Let's say A is the set C, A, R. Let's say B is the set C, A, R, T. Let's say C is the set A, R, T. Let's say D is the set T, A, R. And let's say E is the empty set. And now I want to know, is A a subset of B? Is every element of A, the C, the A, and the R, also an element of B?
Yes.
Yeah.
Yeah, everything in A is in B. So that's cool. How about the other way? Is B a subset of A? Is everything in B inside of A?
No.
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 B has an extra element. It has that T that's not in A. Is C a subset of B?
Yes.
Yes. Is B a subset of C?
No.
No.
Yeah.
How about, yeah, I don't think B is a subset of C because B's got the A, the R, and the T, but it also has that letter C that's not inside set C. I apologize. I didn't mean to have the naming confuse you that way. The letter C is in set B. The letter C is not in set C. Is C a subset of A? Is every letter A, R, T in the set CAR?
No.
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 Is C a subset of D? Is everything inside set C also inside set D?
Yes.
Yeah.
Is D a subset of C? The letter T, the letter A, and the letter R, all in the set C.
Yes.
And so do you see, if C is a subset of D and D is a subset of C, won't it mean that C is equal to D? We have the same elements if each one is inside the other. We could also say that C is a subset of C. Any set is a subset of itself. One that usually kind of blows people's minds a little bit is if I start looking at set E. Is E a subset of, let's say, A? Is everything in E also in A?
No.
Oh,
No.
Why not? What's in E that is
Nothing.
not in A? Like over here, we said that B was not a subset of A because B had that T and T wasn't in A. Is there anything in the empty set that's not in A? Does the empty set have any extra elements above and beyond what's in A?
No.
No. And
No.
so where does it sound?
No. So it is.
It's going to be true. And the empty set will be a subset of every set. You could say that E is a subset of B. The empty set will be a subset of every set. But again, that's not reversed. B would not be a subset of B because B's got stuff in it. That's not in E, the empty set. Let's look at another example. Let's say L is the set A, B, C, D, dot, 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 X, Y, Z. Let's say V is the set of vowels. And in this class, when we talk about the vowels, we are talking about the A, E, I, O, U. We're not doing the sometimes thing. It's just A, E, I, O, U. Let's have C be the set of all C, such that C is a consonant. Just a quick question. Does everybody know what I mean by consonant? Those are the letters that are not vowels. So it would be like B, C, D, F, G, H, J, K, L, M, N, Q, R, S, T, V, W, X, Y, and Z. It's the rest of the alphabet stuff that's not a vowel. No. Is V a subset of L? Excuse me.
Bless you.
God bless you.
Thank
Bless you.
Thank you. Are all of the vowels in the alphabet?
Yes.
Yes.
Is L a subset of V? Is all of the alphabet a vowel?
No.
No, so we'll say it's not a subset. Is C a subset of L? Are the consonants letters in the alphabet?
Yes.
Is V a subset of V? Are all the vowels in the set of vowels?
Yeah.
Is C a subset of V? Are all of the consonant vowels?
No.
No. And is the empty set a subset of the alphabet?
Yes.
Yes. Now here's one that gets tricky. Is lowercase a subset of V? Let's look at this lowercase a. Is that lowercase a set?
No.
No. So it's not a
No,
set.
it's a vowel.
If I wrote it a like that, then it is a subset. Or I could say that a is an element of a V without the braces around it. So be careful notation wise. In order to be a subset, it must be a set. If it's not a set, and I'm comparing it to a set, the only type of comparison that I can make is whether it's an element or not. Now, where we're going next is a variation on this theme, but I'm just thinking let's make sure that everybody gets a subset down conceptually before we add to it a different type of subset, a proper subset. So we've got 4 minutes left, but I don't want to cram a whole bunch of something different in those last 4 minutes. So let's stop here. What we've done thus far, you should be able to complete all of that homework assignment. Homework 1, homework 2, you should be able to work with in terms of subsets, as long as that symbol has a little line underneath it. If it doesn't, we didn't get to the meaning of that yet. So, back away from those questions. Does anybody have any questions on what we've done today, or anything at all that we talked about this semester?
So section 2, what we just went over, that's not
We haven't finished all of section 2, and that's homework 2.
okay.
We finished everything in homework 1.
Okay.
And if anybody came in late, please stick around for a minute and let me know that you came in late so I get you on attendance. Otherwise, you won't get credit for being here. And otherwise, have a great day. We'll see you guys on Wednesday.
All right. Have a good one.
Have a nice day.
Bye, you too.
Anybody who's left get here a little bit late.
Yes, I think I came in like 3 minutes late.
Okay, and I am looking in, oh, you know what? I think I did mark that you were here with attendance, and I have to apologize. In my roster, your name is reversed. So could you please help me again? What name would you like to be called by?
Zainab.
Zena?
Yes.
Okay, thank you. Hopefully I'll remember that next class.
Okay.
All right, have a great one.
You too.
Okay, bye-bye. Everybody else, any questions?
I came in like a minute or two late. I just didn't know if
Mackenzie, yes, I got you. I saw you in the waiting room and I let you in.
Okay, thank you. Have a good one.
You too. Anybody else have any questions?
Yes, I would like to set up a meeting with you one-on-one.
Okay. What time works for you?
Are we doing it today or tomorrow?
Your call. Tomorrow, my scheduled office hour is from 11 to 12. I could also be available a little bit later than that. Today I teach until just about 2, so I could be available after 2.
Can we do tomorrow since I have to study for a biology quiz for tomorrow?
Sure. And is 11 o'clock tomorrow fine or no?
Let me look real quick. I want to make sure. Tomorrow's the 26th. And
Yeah.
you said 11, right? Yep,
Right.
that's perfect.
Okay, all right. The link for my office hour is in Blackboard. It's on the in the left-hand menu, pardon me. I added a separate link that's called office hour. You can just click on that.
Okay, so it'll be like a Zoom meeting too, right?
Right.
As well. Okay, I look
Right.
forward to meet with you tomorrow. Have a
Okay,
great day.
sounds good. You too.
Thanks, bye-bye.
Bye-bye. William, how are you? Are you there? Okay, I'm gonna end meeting. Bye-bye.